So lecture number 16, exploitation versus exploration. We talked a little bit about this at the end of the last lecture and gave a little example, but we're going to dive into a bit more of the mathematics of that today in the form of bandit algorithms. And so let's get started with that. So as I said last time, one of the main challenges in reinforcement learning and in real life is this balance between exploitation and exploration. And so to obtain a lot of reward, of course, you have to take the actions that you know or you think you know have a good reward. But in order to know which actions have a good reward, you have to actually try them, right? And so you have to exploit the knowledge that you have, but you also have to explore the knowledge that you're not sure or you don't know that you have yet. And so there's this balance. And this, in my opinion, is one of the main challenges of real life as well, right? You go through every day kind of wearing the clothes that you're comfortable in, talking to the friends that you've had for a long time. You know, it's the same thing in relationships, with eating, with a whole bunch of different things, right? City you live in, thing you do at school. You're doing the thing that you're familiar with that you think will give you good results, but how do you know for sure if you haven't tried other things? So to know something and then to know something more, that's pretty much this process of learning, right? And so learning, I'm sure it has a million different definitions, but in my opinion, learning is the process of gaining new or modifying existing knowledge, right? I knew something before, and now I'm the same person at a different time step of my life, and now I know something slightly different. And so we've learned something if we have information that we didn't have before. I think that's a pretty basic definition of learning. But the cool thing is, in my opinion, even though if we go through life and we get some knowledge that was the same as knowledge that we previously had, even though it's the same thing that we knew, we are still learning. How are we learning if it's something that we knew before? Well, the variance goes down, right? So if we keep seeing the same thing over and over, then we are more certain of that thing. So just imagine that you saw something, you know, and you learned something or you took an action somewhere and you keep getting the value of 100. Okay, now I'm more certain every time that the value is 100. But if I see it 100, 0, 100, 0, you know, every time you see something, you gain more knowledge, even if it's the same thing that you saw before. So exploitation then is exploiting that current knowledge. So we're choosing high-valued actions for which we already know or we already have a value. When I say know a value here, I don't necessarily have to know the true value, the true expected value, but I have some belief of that value at a particular time step. And so exploitation, we would say this is low risk and possibly low reward, because we are pretty sure that we know what we're going to get, but we're not certain that it might be the highest thing, right, over time. So always choosing actions that we are familiar with gives us a little bit of reward, but it gives us very little new information, just like in real life. If I always go to the same restaurant, I never figure out what's out there. Exploration, on the other hand, is trying actions either that we haven't tried before, or maybe we did try them before, but we're very uncertain about what the value of those actions is. So it's just trying different actions. And trying the actions helps us learn about their values, and then it's possible that new actions have higher rewards than the ones that we've previously selected, right? But it's also possible that they have much lower rewards than previously selected. But we won't know that until we try them. And so once we have explored sufficiently, then we can exploit the knowledge that we have and be pretty certain that we're doing the best thing. So the example that we're going to use here is called the N-Armed Bandit problem. Has anyone here ever played a slot machine before? Yeah, only one person. Good. None of you are gamblers. But essentially, these slot machines at a casino typically, or online now, you know, that's where most people play them. You put in $1, you pull a lever, and then you have a very high probability of your money being stolen, right? And you have a very low probability of getting more money out than you put in. And so that's how the casino makes money, is that these machines are, the expected value is negative. You are expected to lose money over time. And so a friend of mine would walk into a casino and get lucky and win like $30 and then proceed to put the whole $30 in, right, and just lose the money that he made. But if you're ever up money on a slot machine, just walk away. Now, there's some argument to be made for, okay, I'm paying for the entertainment value, right? Like, instead of watching a movie, I'm playing a slot machine, but that's up to the user. But anyway, the reason they're called bandits, some drilling going on in the next room, the reason this is called the bandit problem is because they're stealing your money, right? So they're bandits, they're robbers. And the reason it's called the N-Armed Bandit problem is because there's N of these things. And the slot machines are called the one-armed bandit because it's robbing you and it only has one arm. That's the arm that you're pulling. So in the N-Armed Bandit problem, you're repeatedly making a choice among N different actions, right? So I have N different slot machines. Which lever do I pull? That is the analogy to real life. Do I go forward? Do I go left? Do I eat at that restaurant? Do I eat at that restaurant? You're pulling a slot machine, right? But in real life, your odds of getting a decent return are probably just a bit better than an actual slot machine. After each action, you receive a reward from a stationary probability distribution, depending on the action. I'll talk about what stationary probability distribution means in a little bit, but you get some reward. And the objective is to maximize your expected total reward over a certain number of action selections. So if we have infinite time to do this training, or we have infinite money to play the slot machines, then this doesn't matter. We just choose one of them, then another one, then another one, then another one, and we just play them all an infinite amount of times. But in the real world, we have things like, this has got to be ready by Monday. That's what the boss says. Or I've only got $200 worth of Amazon credits left. Or I've got just a time limit before the assignment is due. So I've got some sort of cost associated with taking an action. Usually that's time or money or whatever. And then I'm trying to learn as much as I can within my budget, right? So that's what this problem is. So what we're going to do is figure out which one we should pull, right? Which action we should take. So the N-Armed Bandit problem is also called the multi-armed bandit problem, and the analogy is to slot machines. You have some limited amount of resource that you're trying to spend in order to learn as much as possible about these bandits so that you can choose the right one. And so the question here is which lever do I pull? And how do I select which lever to pull? And how do I learn, how do I update my values about that process? And this is everywhere. We're going to have an assignment on this where we look at which direction to go in, right? In a grid maze. Which door do I pull in real life? Which job do I take, right? So this is really a problem. I know this is associated with like gambling, but it's just an analogy for every possible problem that exists. So exploitation versus exploration again. If at some point we are maintaining some sort of estimates of the values that actions give us, at any time we have one that's the best, right? So I've got a number, a bunch of actions, I've associated a value with them, and one or more of them just has the highest value at any given time. And if we take that action, if we choose the one with the highest value, that's called the greedy action. So exploitation is just choosing the greedy action, right? I think this one is worth 7, all the rest are less than 7, and so I'm going to choose the one that has 7, and that's the greedy action. And so what this does is it maximizes single action returns based on my current belief of what all these values are. So I'm just going to choose the best one. Exploration then would be choosing an action that is not the greedy action in order to improve my estimates of all the actions in general. And so this is required for future reward maximization, right? So if I'm currently trying to decide on which action to take, and I want to say, okay, I want to maximize my short-term gains, then I'm going to pull the lever which I currently believe is the best, obviously. But if I've got a million levers to pull, I'm probably not just going to keep pulling the greedy one, because then I don't learn anything. So there's this balance between how long you spend learning, possibly taking non-optimal actions, and how many times you pull the greedy action. And so how we balance this is a key issue in reinforcement learning, because this is essentially the problem that reinforcement learning is trying to solve. So the two things that will lead us to how we do this, there's two different things here, and these are the two different exploration versus exploitation concepts. The first one is more mathematical. It's basically just how do we store and update the value estimates as we learn over time, right? So I have some current value estimates for all these actions. I take an action, I get a new reward. How do I update my belief with the, like, what's the mathematics of all that, right? And the second one is sort of a policy or action selection thing, which is now that I have these actions with these values, how do I pick which one that I want to try next, right? And so one way to do this are called action value methods. And so how do we store the current value estimates? That's the first question that we have to ask, right? And so in the literature and in the book, they use this value of Q. Now, I like the epistemology of things. I like knowing where words came from. So sometimes I'll do some research like, why Q, right? It's just interesting. And so this morning, actually, I've asked this question myself a lot. So I sent an email to Rich Sutton, who wrote the book. And I was like, hey, Rich, do you know why Q was chosen? And he replied, actually, like as I was walking over to class. So I just checked my phone, and he said, I'm pretty sure it was arbitrary. But he said Chris Evans was the person whose PhD thesis Q first appeared in, so you can email him if you want. But anyway, here we have Q. So Qt of A is going to be the estimate of Q star of A, where Q star of A is if we had an oracle, if we were God, if we knew the true value of this. That is our current estimate of the actual value of A after time step t, right? Q star of A is the actual value of action A. So if we could do it 1 trillion times and then record the average or whatever, then this is the actual value. So this is the mean reward. And this, of course, is as t goes to infinity. So at some time, step t, I've got an action A. Qt of A is my current estimate of the value of that action. So let's look at an example implementation of this. Let's say we've got the N-Armed Bandit problem. And so QA is going to be the estimate of bandit A's reward. And so choosing a bandit is choosing an action, essentially. So if this N-Armed Bandit problem, I'm just going to label them 1, 2, 3, 4, 5, and then I can choose one of them as my action. So let's say, for example, I've got 4 bandits. Let's just store this in an array, right? Simplest possible thing. If I've got a small enough number of actions that I can just store it, then why not store it in an array like this? So I said Qt of A is our current action value estimate, but of course we've got to start somewhere, right? And so Q0, you've just got to make some decision at what your initial value is, right? So what we'll see is a decent way of doing this is just keep the running average. And if you're going to keep a running average, then let's start at 0, right? So let's just say that our estimates of the value of all of these actions are going to be 0 initially. Now, sometimes you might want to do that. Sometimes you might not want to do that. We'll see more of that as we go on. But then at some point, after t time steps, these values have changed, and we now have these beliefs of the actions of each, or the values of each action, right? So if I were to say, okay, which action are you going to pull next? You might say, well, maybe I'll choose that third action because it has the highest value, right? That would be the greedy action selection. Or maybe saying, I've been pulling that one a lot. Maybe I'm not sure of that first one. Maybe I'll choose that first action to see if its value updates, right? So let's look at an example of this. So I did out an illustrated example, and let's step through it. So here, what I did was, if you're watching this on the video, there's those of us who don't come to class, my face is probably covering the bandit here, but it just says the number 4 on it, right? So that you're not missing anything because my face is up there. So up here on the top row, we've got our 4 different bandits. And of course, this is just an example of 4. You can have as many as you want. 1, 2, 3, and 4. And that's associated with action A. So bandit 1 is action 1, bandit 2 is action 2, and one action is just pulling the lever one time and getting a single reward from that thing. Then I've got this thing called a distribution, which I'll get to in a second. Then I've got rewards. So as I pull each slot machine, as I take actions, I'm just going to keep a list of all the rewards that I got, and I'll put them there on the slide. And then down on the bottom, I've got my values, Qt, and so whatever my current value estimate is of each slot machine, I'm just going to write on the bottom, right? So this is just an easy way of looking at it. What do I mean here by distribution? Well, you can think that there's an infinite number of distributions, right? So for example, I could pull on a slot machine where I always lose. I could pull on one where I always win. I could pull on one where I win 17.2% of the time. And so what I've done here is I've just for, imagination's sake, for excitement's sake, put in some different distributions here. So whenever I pull on this lever, I'm always going to get a 5. This one, I'm either going to get negative 20 or 20. This one, I'm going to get a random number between 0 and 10. And this one, I'm going to get a random number between negative 10 and 10. So the point here is that these are the distributions of these slot machines. But if we were to do reinforcement learning on a problem, we probably don't know the distributions, right? Because if we knew the distribution, we could just do some numerical statistic analysis on these and just choose the best one, right? So just tell me which one you might pick if, hand up, which of these would you pick if you had to pick one? Hand up, I hear some whispering. Yep.
I would pick 3, number 3, because it's positive.
Yep. Sure. So you look at number 3 and you say, okay, it's always going to be between 0 and 10, so I'm always going to be getting something. That's a good example. You had a hand up. Were you going to say the same thing?
No, I would go with number 2 because it's kind of like maybe if it is gambling, I will prefer to reward.
So we've got a gambler in the audience, right? So if you get really lucky, then number 2 is going to be the thing that could possibly pay off the highest, right? I saw you making a move.
Number 1.
Oh, great! We've got a number 1 as well.
Because you're always getting 5, but number 3 is like you could get less than 5.
Yep.
More than 5, so this one is like you're consistently getting the same one.
Okay, so we've got the person who just wants something good every time, the person who wants to gamble, and the person who wants to know their paycheck every week, right? So these are all valid human reasons for wanting to do this, right? But if we were to pull these 1,000,000 times, would your answer change? Right? So this is, yeah, it might. So if you're going to pull it okay a couple of times, sure, maybe I'll get lucky. But let's talk about how this actually works out. Okay. So the thing that we have to do here is that we're going to have some initial value, right? Q0 of 1, Q0 of 2, Q0 of 3, Q0 of 4. Let's just set them all to 0. How do we, once we get a reward from each one, how do we actually update those values? So that's the question that we have to ask. So the first way, there's a couple of different ways we can do this. There's probably an infinite number of ways, but we're just going to talk about a couple. First is sample average estimation. And so QT of A, sample average estimation, I'm sure you can all figure out the formula for this. So just the natural way of calculating QT of A is to average the rewards that we received, right, after a certain number of plays. Averaging is good. It's statistically valid. It's the mean value. It's what we would expect over time. So as you play, if at play T, action A has been pulled Ka times, so K is the counter for how many times we've pulled a particular action, yielding these rewards, R1, R2, up to RKA, then QT of A is just the sum of everything, sum of all the rewards, divided by the number of rewards. Just the average formula. You all knew that already. And so if K is 0, then define it as some default. Let's just use 0 for now. And as Ka gets large, QT of A is going to converge to the true value, right? Because the true value is the mean value. That is our expected value if we pull this at any point in time. And so the average of the samples is the sample average method. What a creative title for this method, right? So let's have a look at the sample average method. So here is we are going to pull, let's just pull them from left to right. Okay, so we're not talking about how we select the actions right now. We're just talking about the update. So let's just say we're going to pull from left to right. So I'm going to pull action number 1, and surprise, surprise, I got a 5, right? Because I always get 5. So this is time step 1 now. And at time step 1, I average up all of these, so I sum all of these and divide it by the number of them. So 5 divided by 1 is just 5, right? Okay, let's go to the next one. Oops, I got unlucky the first time I pulled this one, so my average at Q2 is now negative 20. Over here, I got a 4. It's all right, it's in the middle, so my average is 4. Over here, I got an 8. Oh, I got really lucky there, right? Next, I pull this one again. Surprise, I got another 5. This one, oh, okay, I got a 20, so it evened out. Here, I get a 0 this time, so I got kind of unlucky with that one. So my average of those two is now 2. And over here, I got pretty unlucky, or a little bit unlucky, I got a -2, so my average is now 3. Okay? So a -2 divided by 2 is 3. So this is the sample average method, super easy. And now, at some point, we've got these values, right? And so my choice, if I were to choose, I don't know these distributions, right? Which one do I choose next? Well, maybe I would be pulling that always 5 one. But if I had gotten lucky twice with the 20, maybe I would be pulling that one, right? But our beliefs of these values are going to change over time, and so how do we deal with that? That's another thing that we have to deal with. A second way of doing this is called the incremental update estimation. So recall that this is the formula that calculates the average, right? What might be a problem with implementing this formula over time? Anyone?
Any random analysis that you make after a certain number of k won't really affect the average then?
Well, that's more of a problem with how averages work. But the thing I'm sort of looking at here, it's fine that you don't realize it right away, is that we have to store all the rewards. And if we're learning, if like we write some C++ program to like do this really, really fast, we've got billions or trillions of rewards within a few seconds. And I can do trillions of calculations, but it's kind of hard to store trillions of things. And one of the problems here is that as I keep pulling levers, then every lever that I pull takes longer to calculate than the last one, because I'm adding to this list and I have to sum up the list every time. And so ideally, we can escape that. So we need to store all of the rewards. That's a bad thing when I'm calculating the average of something in that naive way. So the problem is that the memory and computational requirements grow over time when I'm doing something like this. So let's derive an incremental formula so that memory is no longer an issue. So what we have right now is that the new average, after I pull a new thing, is a function of the history of all the samples. So I have to keep that whole list of all the samples. But what I really want it to be is a function of just the old average and the new sample. So I keep a fixed amount of memory and a fixed computation for every pull. So let's look at how we can do that. And I'm sure that everyone in here could probably derive the formula for incremental average, but let's have a look. So this is a little bit small, apologies, but we're just going to have to deal with that. So QK, that is my current value estimate. And so this is the formula for an average, just summing everything up and dividing it by k. Let's put that into summation form, because as mathematicians and computer scientists, we want to get the easiest way to look at something. So we've got 1 over k, and then the sum from I equals 1 to k of r sub I, right? Pretty easy. But what we're trying to do here is get a formula for rk plus 1 that's dependent on, a formula for qk plus 1 that's dependent on qk instead of this history of samples. So here, qk plus 1, well, we've got the formula for qk, so let's just sub in k plus 1 for k. And so this is it here. But what we see is this qk plus 1, this formula, still depends on the history of all the samples, right? So let's do some math moving stuff around. So let's separate this term in here, which is like the sum from I equal to k plus 1. So we're going to separate that into just the k plus 1 term plus the summation from I to k. Okay, some of you are already nodding. You can see where this is going. Then what we're going to do is this is the sum from I equals 1 to k of ri. But if we look up here, sum I equals 1 to k of ri, that is k times qk, right? Because this whole thing is divided by k. So this is k times qk. Okay, we're getting there. So now what we're going to do is I'm going to do the mathematical trick where I add something and the negative of something. So here I've got k qk. I'm just going to add qk and subtract qk so that I can factor that k plus 1 outside. And so now I've got k plus 1 times qk minus qk. And what that allows me to do is now I've got this here, and I've got this here, this k plus 1. So I've got something on the top and something on the bottom. So I can take this qk outside, and now I've got these terms that are left. Okay? So what we've done here is we have very simply derived the formula to incrementally update an average. Okay? So the average of the next thing is equal to the previous average plus 1 divided by k plus 1 times the new reward minus the old average. Okay? So that's how we do that. So the incremental implementation, qk is the average of the first k rewards. Qk plus 1 was equal to this, which we derived to be equal to this. And now we've got exactly what we want, which is the new estimate is a function of the old estimate. This value, which is the only thing we need to store, which is like the number of times that we've pulled it, and the old value. Perfect. So what this does, this is in the form of function of what we have here, which is that the new estimate is equal to the old estimate plus some step size. That step size happens to be 1 over k plus 1, okay, times the new sample minus the old estimate. So what we're seeing here is that the incremental formula basically says, I've got a new estimate, I had a previous estimate, let's find the difference between those, and then this step size is going to be how much do I trust the value of the new sample, right? Well, if we want to store the average of something, then our trust in every single one of them is going to be the same, right? So our trust in each one is identical, which is 1 over k plus 1. And so in this case, the new sample is referred to as the target value because we've got a new target, and essentially we had an old belief and we have a new sample, and pretty much what you can intuit of what's going to happen is we got an old belief, a new sample. Our belief is going to go somewhere from the old belief toward the new sample. But how far it goes toward the new sample is, up to you to decide. Another question is, what if our distribution changes dramatically? So what if, for example, we had always 5 for 1,000,000 pulls, right? And then someone updated the firmware of the slot machine so that it's always negative 100, right? So, okay, we've got always 5 for 1,000,000 pulls. We're doing an average. The first time we pull negative 100, well, my average was 5. What's my new average? It's like basically 5, right? Because my previous sum was 5 million divided by 1,000,000 is 5. Now I've got 4,999,990 divided by 1,000,001. It's basically still 5, right? So the incremental average is great for stationary distributions. If you know 100% that your distribution will never change, right? It's the same thing all the time, then the average is fine. But in the real world, doing the same thing in the same situation may not always yield the same results, right? Maybe, doing the same thing outside if there's snow is different if there's no snow, right? So you've got to be able to, well, in some situations you want to be able to account if your distribution changes dramatically. So if the distributions remain the same, the problem is called stationary. If the distributions are allowed to change over time, it's called non-stationary. Okay? So imagine having an average of 1 for 1,000,000 time steps. If we change to 100, updating that average would be very slow, right? We've got to have hundreds of thousands, if not millions of more pulls in order to start believing that it's now 100. So for non-stationary problems, averaging really works fine only for stationary rewards, but not if it changes over time. And so what we want to maybe do is something like, instead of trusting the weight of every sample that we've ever gotten equally, let's weight recent rewards more than old ones. So we can trust the things we've seen more recently more than the things we've seen in the past, because if things have changed, we do want to trust the things that we've seen more recently. And so what we're going to do is we're going to come up with this value of alpha, and that is a step size parameter. This has nothing to do with alpha beta. This is just the number that they use in the literature for this. And so this alpha is going to be between 0 and 1. And so our new estimate is going to be the old estimate plus alpha times the difference between the new value and the old value. So let's have a look at that in an example. So here's the formula that we have. And so essentially, the new estimate is pulled toward the reward by alpha. So let's look at an example. If QK, if my previous belief was 50, and my alpha is 1, and my new reward is 100, then what we're going to see is, if alpha is 1, we are going to trust the new one completely, and our new value will be 100. If our alpha is 0, we're not going to trust the new one at all, and we're going to just keep the same belief. And then alpha, if it's 0.5, it's going to go halfway. If it's 0.75, it's going to go 3/4 of the way, etc. So here, we've got 50 plus 1 times the difference, and if you've got the old thing plus the difference, that's just the new thing, right? So that's 100. And so if we have alpha equal to 0.5, then intuitively, our new belief is going to be halfway between the old belief and the new reward. So here, 0.5 times the difference, well, we're adding 25 to get us to 75. So we went from 50 to 75. So just to illustrate that a little bit more, to drive it home, if we have QK of 50, and we have a new sample of 100, and this is alpha. So if alpha is 0, we stay at 50. If alpha is 1, we go all the way to the new sample. If alpha is anything in between, that's how far we go, right? So here, if alpha is 0.5, we would go halfway, et cetera, et cetera. So that's what alpha means in this case. So let's look at an example where we are now doing an incremental update method instead of sample average method with alpha equal to 0.5. So as before, we always get 5 from this one. So you can see that if you have something that's a stationary distribution that always gives you the same reward, this is never actually going to get you to the true value, is it? Because we're always going halfway, and we never actually reach the finish line. It's like that old story of, that if you shoot an arrow at somebody, right, it's going to go half the distance at some point, and then it's going to go half the distance again, and then it has to go half that distance again, and so it'll never reach you, so you're fine. Right? So that's the calculus jokes about limits, but anyway, you didn't take calculus, obviously. So here, the interesting thing is, we will never actually reach 5, because we always go halfway toward 5, but we never quite get there. But negative 20, we went halfway between 0 and negative 20, which is negative 10. Over here, we got a 4, so we go halfway between 0 and 4, which is 2. Here, we got an 8, halfway is 4. Here we got another 5, so we go halfway between 2.5 and 5, so it's 3.75. Here we got a 20. And look at this. This is really interesting. Before, we had negative 20 and 20. The average was 0. Now we have negative 20 and 20, and the value is 5. And the reason is order matters now. The order in which we receive the reward matters because we no longer weight them all the same. So if we had gotten 20 and then negative 20, our belief here would be negative 5, because we trust the more recent negative 20 more than we trust the least recent 20, right? So over here, we get a 0, so we go from 2, halfway from 2 to 0, which is 1. Here we get negative 2, halfway from 4 to negative 2 is 1. So that is the difference between these. And so this is what we get, Q8, 5, 0, 2, 3. So me giving you something like this on an exam would be perfectly fine. You should know how to do that calculation. Hint, hint. Okay. So those are some of the ways in which we have a belief of a value of an action, and then we take an action, we get a new reward, and then we update our beliefs. Okay, so that was that first part. Now, there are many other ways to do this that involve way more fancy statistics, but I'm just showing you the more basic ones. Now, the real problem is, these are called action selection methods. Which action do we choose, right? So I've got these here. Which one do I choose? Well, if you were to look at just these and no other information, maybe you would choose this one, right, for example. So we talked about greedy action selection a little bit. How do we select an action from our value estimates? The simplest way is to just choose the biggest one. That's it. Just choose the biggest one. So on play T, choose a greedy action A star for which, mathematically, we maximize the action So the action which maximizes Qt over all the actions, right? So that's the one we want to choose. This method always exploits current knowledge to maximize immediate reward. We do no sampling or exploration to determine values of any other action to see if they're better. So we just always keep choosing the best one. Now, look at what this can lead to. Well, if our initial values were 0 and we got a 5, well, we're just always going to choose action 1. We're never going to choose anything else. They could be returning 1,000,000, right? And so this could be a problem. So what you'll see in practice, what some people do, is say, okay, I'm going to try each action once, and then start choosing the greedy action. But what if we got unlucky in another one, right? So you can't just always choose the greedy action. You can't just try everything once. You've got to do something more clever than that. So the next step up in cleverness, I guess, is this idea of Epsilon-greedy selection. So to add exploration, we're going to choose a random action with probability epsilon. That's it. It's really that simple. And so in the limit, meaning as t goes to infinity, as the number of plays increase, each action will be sampled infinite times, right? So let's say that we have epsilon equal to 0.1, which means that we're going to choose a random action 10% of the time. Then, even though we're only choosing a random action 10% of the time, 10% of infinity is still infinity, so we will sample everything eventually, right? And so this guarantees, as Ka goes to infinity, Qt of A converges to Q star of A. So this is a method for choosing actions which will guarantee that we will sample everything eventually enough times to get us to the true values. And in theory this works, but in practice it may take a long time to converge, right? Because we're not choosing everything enough, etc. So if a random action is chosen with probability epsilon, that means that we are choosing a greedy action with probability 1 minus epsilon, right? So we've just got some code in our action selection that, let's say, for example, we've got epsilon equal to 0.1. It means we're going to choose a random action 10% of the time, which means we're going to choose the greedy action explicitly 90% of the time, right? But keep in mind, the random action could still choose the greedy action randomly, right? So you may end up choosing the greedy action more than 90% of the time because you've got a little bit of random chance of also choosing the greedy action. So this is a diagram from the book, and what this shows is on the bottom this is the number of time steps, and here this is the average reward over time. And so what this is trying to show is how reward over time increases with various choices of epsilon. Okay? So here the blue line is kind of stationary. This has epsilon equal to 0. It never explores. Okay? So our reward that we're getting over time is just kind of stagnant, right? Here, this green one, epsilon is equal to 0.1, and the red one, epsilon is equal to 0.01. So the green one on top is exploring 10% of the time. The red one on bottom is exploring 1% of the time. So you can see here that if you explore more, then you're learning faster, right? Because you're exploring more often. If you explore less, well, you're still doing better than no exploring, but if you're exploring 1% of the time versus 10% of the time, you're learning a bit slower. But the problem is, once you've learned a bunch of stuff, the 0.1 is still doing random actions 10% of the time, right? So it's throwing away like 10% of the reward that it could be getting, rough calculation. And so what you'll see if this graph went on a bit more is that even though it took the 1% exploration longer to explore, once it catches up in the learning, it's only exploring 1% of the time. And so ideally, once you've done all the exploring that you need to do to get the, close to the true values, then you're not exploring very much anymore. And so in practice, what you'll see a lot of methods do is actually choose some initial high value of epsilon and then maybe slow it down over time. So lower it over time rather than keeping it constant, right? So here, that's the main point of this slide, is to show that higher values of epsilon explore more and learn faster, but they will not get an eventual reward that is higher than a lower learning rate. The lower learning rates won't learn as fast, but they will eventually get more reward because they're exploring less. So there's a trade-off in that exploration term as well. It's the learning rate versus overall reward. Here's a slightly different graph where this is the time steps on the bottom, and this is not the total reward, but this is the percentage of times that we chose the optimal action, right? So this is the number of times that the true optimal action was chosen. So if we look at this and let's say, okay, there's like 10 total actions, then what you see here is this green one, still at 10% exploration, is finding the optimal action to choose more of the time because it's exploring more, right? So it has learned faster. This red line is not exploring as much, so it's not choosing the optimal action as much. But again, if this graph was bigger, what you would see is that eventually, let's say we have 10 actions and our exploration was 0.1. So 10% of the time we're choosing something random. What is the most that we could theoretically possibly choose the optimal action? 90% of the time. If we're choosing a random action 10% of the time, then 91% of the time, because we still have a small chance of picking the max action. So you've got that 10% gap there at the top because it's still exploring. So 10% of the time, we are not choosing the optimal action simply because we're still exploring that much. But we learned how to get there faster. The 1%, just like the other one, will take a long time to learn what the optimal action is, but then we'll be choosing the optimal action 99% of the time, right? So again, this is just to show that relationship between the epsilon and the reward over time, or selecting the action over time. So here's the overall algorithm for like bandit algorithms. So choose a value update method. Maybe it's the average method if you know that's a stationary distribution. Maybe you want that fixed size step alpha if you know it's a dynamic or a non-stationary distribution. Then you choose an action selection method. Maybe you're going to choose greedy. Maybe you're going to choose a particular value of epsilon. And then you repeat until some termination condition, until your Amazon credits are gone. Choose an action to perform. Get the reward from the bandit. Update the value for your action. That's it. That's the very simple process. And in essence, this is what reinforcement learning does. Now, different methods may not actually record the value. They just may record the action, like this is the best action. But this is the overall thing that's happening. So let's have a look at the actual implementation. Let's say we chose the incremental average formula, and we chose Epsilon-greedy. What would that pseudocode look like? Okay, so here's our bandit algorithm on those bandits. We've got our Q values, which are going to be set initially to zeros. So we've got a number of zeros. If we had 4 bandits, this will be an array of size 4, all set to 0. Now we've got n. This n is actually the other k. So n is the number of times that we've pulled each bandit. So that's initially going to be 0. Each time we pull a bandit, we're just going to increment that by 1 to keep track of how many times we did it. Then while true, I'm going to set this action equal to null initially, and then I'm going to set it with something. So I've got my epsilon. So rand here assumes that it's picking a value between 0 and 1. Okay? So if this random value between 0 and 1 is less than epsilon, then my action is going to be a random action, right? So if epsilon is 0.1, this is going to fire about 10% of the time, right? Otherwise, my action that I'm choosing, I look over all the values, and I choose the index, or I choose the action which has the maximum possible value. And then my reward that I'm going to get is I'm going to take the bandit at that action. So the action is just the index in this case because I'm storing the bandits in an array, whatever, and then I get the value of that. So let's say I looked through, my epsilon was 0.1, my random number was 0.3. Okay, so I'm not choosing a random action this time, and I saw that action number 2 had the highest value, so I pull the lever from number 2 and I get a value. And I also increase n action, so that means that I have tried this action this number of times, so I'm going to increase that by 1. And then my QA, which is my current belief, right? So before, in my formula, I had a QK and a QK plus 1. But of course, when we write actual code with an array, the new value is going to just take the old value. So it works itself out. So QA, which will be the new value, is going to be the old value plus 1 divided by NA, that was the old K plus 1, times R minus QA. So that's it. That's how you would implement the incremental average plus epsilon-greedy selection. And I mean, I could have given you that as the second slide in the previous lecture, right? Why are you going through all this, Dave? Like, just give us the code. Well, if I just gave you that, maybe you wouldn't really understand. Like, hopefully I'm trying to teach you, not just get you to regurgitate something for an exam. I want you to know, like, why this is happening, why we make these choices, and the implications of something like, what if I choose epsilon, right, as a different value? Why did it, hey, I had good results at first, but now they're worse? How can one be better than the other? I want you to, like, understand what's going on here. Why am I always choosing the same action if I'm doing greedy selection? Why is it not moving, right? Okay. Here's another method for doing this, which is called upper confidence bound, or UCB. So exploration is needed because there's uncertainty about the accuracy of our estimates, right? We can never be certain that these estimates are true. Greedy looks good now, might not be best in the future. Epsilon-greedy explores, but it explores randomly, right? Who has ever truly made an important decision randomly, right? Like, yeah, okay, exploration versus exploitation. I talk about choosing another restaurant. You don't just choose from every restaurant that exists. You're going to look at them. You're going to be like, okay, I haven't been there before, but someone told me something about it, etc., right? So it would be better to select among the non-greedy actions that may be close to optimal with some measure about how certain we are about their values, right? There's a whole field of statistics that talks about certainty. So let's factor certainty into it somehow. And so the UCB selection method tries to do this. Okay? Here's the formula that is completely cut off by my face, but you have the slides, right, if you're watching this online. So it says AT equals argmax A, and then in brackets QT of A plus C, square root of natural log of T divided by NT of A. What in the hell is that doing? Okay, we'll go through term by term, and hopefully it will make a bit of sense. ln of t is a natural log of t. T is the total number of time steps. So it's a total number of actions that we have selected.
Unlock your device first.
Thank you, Google. That is the total number of actions that we have selected. NT of A is the number of times that action A was selected. So there's a difference between T and NT. T is the total number of times we've chosen any actions. NT is the number of times we've chosen A specifically, right? And so let's just quickly see the number of times we've chosen anything divided by the number of times we've chosen a specific thing. What is that measuring? Well, if I've chosen 100 actions total, and I've chosen a specific action 99 of those 100, then I'm pretty certain, relatively, about that action versus the action that I chose one time out of 100, right? So total number divided by specific number, that is a measure of uncertainty, right? So if it's 100 divided by 99, that's around 1. If it's 100 divided by 1, that's around 100. So I'm way more uncertain about the values I've selected less than the values I've selected more. So the term within the square root is uncertainty. C controls a degree of exploration. Okay? So look, it's, let me just go through these and I'll explain it in total. Typically what we do is we try all the values once first so that I do have an NT which is not 0 so I don't crash the program. The square root term is uncertainty. So we look at square roots in terms of variance and stuff in statistics for action value A. And the function calculates a sort of upper bound on the possible true value of A and you can vary this C term for exploration. So as NT increases, the uncertainty goes down. When T increases but not NT, the uncertainty goes up. So what this does is it tries to factor in the uncertainty of an action, right? So we want to pull the things, so we're trying to maximize the action that maximizes this value, right? In here, it contains the actual value, right? So the value is important. We want to pull high-valued things more often, right? Even though we're exploring, we still want to be pulling the high-valued thing to get the reward while we're exploring. We don't want to only explore, but we do want to explore sometimes. So we have this uncertainty term, and we have this value of C. So if C is 0, we never explore. If C is infinity, then what we choose here is just the action that we have chosen the least amount of times. But if C is somewhere between like 0.5 and 3 or something like that, those are typically the values that I've seen. Those are things where we can truly balance the value of, okay, I want to pull things or select things that have given me good values, but also explore with respect to the uncertainty. Okay, so this is what the UCB formula attempts to do. And it has been shown that over time, it can do slightly better than, or it can do better than Epsilon-greedy. Theoretically, it has really nice properties. In practice, it does take a while to converge. Okay? And so that was just to show you that this is UCB, and I think this is actually technically UCB1. There's different variants of the UCB formula. I think this is UCB1, but it's just another way of doing that action selection rather than just saying try something at random. Okay. Next is QA versus QSA. So QA is the value of doing action A. But this kind of assumes that we only have one state in our environment, right? I'm just here and I've got 4 actions. I'm sitting in front of 4 doors. I'm sitting in front of 4 slot machines. There's no states there. It's just the value of an action. So this is the value. The value of a specific action will vary depending on the state that it was issued at, right? So if I'm right next to if I'm to the right of the goal, then the value of doing left is way different than if I'm on the left-hand side of the goal. So typically, we're going to be, so moving up is good if the goal is up, but not if the goal is down. So QSA is typically what we're going to be looking at. We never use just Q of A, right? It's Q of SA. What is the value of doing this action at this state? So QS of A is the value of doing action A at state S. So if we look back at the examples that we've been doing before, so, pathfinding, for example, up, down, left, and right movement. This is a particular state. These are my actions, right? Action 0, action 1, action 2, action 3. And this is how we're going to be solving that problem. We look at this as the N-Armed Bandit problem. So each of these are actions. Each of these are slot machines. We keep trying actions at particular states. They're going to give us rewards. And we look at those, and we calculate the values, and then we pick actions based on their values. And so these are the values QS of A. So this is QS of 0, QS of 1, QS of 2, QS of 3, etc. All right. So, that's it for the lecture, but some possible exam questions. What are the formulas for the average and incremental update? Be able to do all the math that I did in the slides, right? That's pretty expected. Be able to describe exploitation versus exploration. I will probably, if I was going to ask a question, maybe give an example, but one that's not in the slides. So if you're studying, think of one that's not a restaurant, right? Think of one that's not buying a house, the 2 examples that we talk about. There are lots of them, so just try and think of one. Action selection methods. So greedy, Epsilon-greedy, upper confidence bound. What is the effect of my learning as epsilon goes up or down, etc. And the pseudocode for that bandit algorithm should be no problem for you.